Welcome to the third pre-recording of the Programming Languages virtual meetup. My name is Connor Hoekstra, and in this pre-recording, we're going to be covering the third and final part of the first chapter of the book, The Structure and Interpretation of Computer Programs. Before we jump into the content and summary of the last part of this chapter, a couple things. The last meeting had individuals from 4 different countries tuning in, or at least the ones that responded to the question when I asked, where are you at? So those individuals were from the United States, Canada, India, and Denmark. And the primary languages that these individuals were using were the following 7, C++, JavaScript, C#, Python, TypeScript, Racket, and Rust. So in aggregate, over the first 2 meetings, we've had people tune in from 7 different countries and people using 11 different programming languages. So awesome to know that we've got a diversity of people from different countries and with different experiences tuning in because it creates a better conversation. The last 2 things, Discord, link to the Discord in the description down below. It goes stale, so as I've mentioned before, if it's not working for you, head over to the meetup page and just leave a comment and I'll post a new Discord link. And last but not least, there is a Twitter for this Programming Languages virtual meetup, so if you want, go and follow that on Twitter. So let's jump into the final and third part of Chapter 1 of SICP. This is the table of contents. The title of this last part is Formulating Abstractions with Higher Order Procedures. The 4 subsections: procedures as arguments, constructing procedures using Lambda, procedures as general methods, and procedures as return values. So similar to the second part of this chapter, this is mostly going to be a chapter by example. We're going to go over a lot of the exercises that the part of this chapter presents us with, and hopefully by the end of it, you'll get a good sense of what this chapter is trying to cover. So the first example that the book covers and the authors cover are these 2 different examples of functions, sum integers and sum cubes. Basically what the sum integers does is it takes upper bound and lower bound and sums all the values in between it. So if a is equal to 0 and b is equal to 10, the result is going to be 55, and you're going to do that just by adding up the numbers and making recursive calls to sum integers. Sum cubes does the exact same thing, except before adding them, it cubes the result. And what the book and the author points out is that these 2 functions are extremely similar. If we compare them side by side, there's only a couple different parts to these functions and everything else is the same. So the first thing that's different is the name of the function. The second thing that's different is the transformation that's being made to the values before summing them. Note that in the first one, we're not doing a transformation, but in the second one, we're cubing the values before adding them together. And then the third thing that's different is the recursive call to the named function, which was different to begin with. And what the author goes on to basically explain is that we can define a function that is an abstraction over these 2 that just passes in the things that are different, and then we can use those to define these functions without having to repeat all the same code. So that's avoiding the DRY, don't repeat yourself. So here is the function quote-unquote abstraction. It's called sum, and it takes 4 parameters or arguments. And those are term, the transformation that we're making to our integer, a, which is the lower bound, b, which is the upper bound, and next, which is a function to increment the values in between a and b. So for the previous 2, they're just incrementing by 1, as you can see, plus 1. But if we wanted, we could step by 2 or do some other kind of increment. And if we use this function abstraction, we can then redefine sum cubes and sum integers as the following. So note that we're defining this inc, short for increment, to do our plus 1 to pass in as the third argument to our sum function. And then sum cubes just becomes sum and then cube a inc b. And so a and b are basically being passed along from the top level function sum cubes. And then for sum integers, because we're not doing a transformation, we have to define a function called identity, which is always just passing along the value itself, so we're not doing anything to it. And then we define some integers as sum identity a inc b. So this is super neat. And if you're familiar with functional programming languages, you'll know that there are a ton of functions. The fold and reduction algorithms are probably the easiest and most common example where you can define algorithms in terms of those folds. So sum is basically the reduction over plus. Product is the reduction over multiplies. maximum is the reduction over the max of two numbers, so on and so forth. So at this point, we're going to skip to exercise 1.30. We'll get back to exercise 1.29 because it's super relevant to what we just covered. So the sum procedure above generates a linear recursion. The procedure can be rewritten so that the sum is performed iteratively. Show how to do this by filling in the missing expressions in the following definition. So potentially you didn't need your handheld with the sort of template of this. But using this template, we can easily define the iterative version of the recursive function that we just defined. So exact same function definition. Your function is called sum. It takes 4 arguments. So the parameters are term, a, next, and b, as we saw before. And then right inside, we're defining our intermediate iterative function, which is just going to take an initial value a and then result, which is going to be our accumulator. So if we get to the point where a is greater than b, we just return the results. Otherwise, we're going to make another call to the intermediate iterative function, and we're going to be incrementing our a with next, and then we're going to be adjusting our accumulator by adding to it the transformation of the current value that we're at, a. And then we're just going to kick off this iterative linear process by making a call to iter, our lower bound a, and then passing it an accumulator initial value of 0 because we're adding numbers up. And then if we once again define inc and identity, we can make a call to sum identity 0 inc 10 and get the correct value of 55. So moving on to the next exercise, it states the sum procedure is only the simplest of a vast number of similar abstractions that can be captured as higher order procedures. Write an analogous procedure called product that returns the product of the values of a function at points over a given range. Show how to define factorial in terms of product. So this is basically the solution. If you compare it to the previous solution, is identical except for 2 things. We now have a multiplication instead of an addition here on the second last line, and the initial value for our result or our accumulator parameter is 1. And that's because when you multiply, if you start with 0, you're going to 0 everything out. So if we do product identity 1 inc 10, this is the equivalent of factorial basically. So pretty straightforward. If you wanted to define factorial, you could just basically hard code the a to be 1. And next is going to be inc, term is going to be identity, and then you're only going to be passing along the upper bound. And so if we move on to the next question of exercise 1.32, it says, show that sum and product are both special cases of a still more general notion called accumulate that combines a collection of terms using some general accumulation function that has accumulate as the name, and then the parameters combiner, null value, term a, next, and b. So shout out to C++. It's the only language that I actually know that calls their reduction algorithm accumulate. So if you are familiar with the C++ algorithms, you'll recognize accumulate. Arguably, this is the wrong name for this function, and it should be fold or reduce, but c'est la vie. And if we go ahead and combine, sort of similar to what we did with some integers and some cubes, the abstraction function over product and sum, we're going to end up with something that looks like the following. So we're defining our function accumulate, taking the 5 parameters as I mentioned before, a combiner, init, term a, next, and b. And then we have, this is an iterative linear solution. So we have our intermediate iterative function inside that very similar to what we did for the iterative sum function. We've got our initial value a and then our accumulator result. So if a is greater than b, we just return the result. Otherwise, we increment a, and then we're going to adjust our accumulator by using the combiner. So in this case, it's either going to be plus or multiplies, depending on what we've passed. And then we're doing our transformation with term. And then once again, we're going to kick this off by making an initial call to the intermediate iterative function iter, passing it the lower bound a, and then passing it the initial value that you've passed in. And so this all becomes a lot more clear when we look at the 2 definitions now, the redefinitions of product and sum. And so unlike the book, I've lined them up, which makes it much easier to tell the differences. So product, you can see, is identical to sum except for in two places. Here we're basically multiplying and passing an initial value for our accumulator of 1. And for the sum, we're passing the plus operator and then starting with an initial value of 0. So this shows you how powerful it is to define these generic algorithms and enable and have arguments that can be passed that customize the behavior ultimately of this algorithm. So accumulate is what it is known as in C++11. In C++17, they came out with a parallel version called std reduce. And in many other languages, this is known as fold, reduce. I believe in C# it's called aggregate. And it's known, I think, inject, it's known as in a couple languages like Smalltalk and Ruby. But this is a very, very common algorithm that enables you to very simply define other reduction algorithms that are just specializations of this reduction behavior. And at this point, we're skipping back to an earlier part of the first section of this last part of the chapter where it talks about Leibniz's formula for an approximation for pi. So I tweeted this out on the weekend because it just made me so happy to see how beautiful this racket code is using algorithms and threading. So if you take a look at the original code that I looked at, basically the formula is 1 over 3 times 5 plus 1 over 7 times 9 plus 1 over 9 times 11. So it has odd numbers as the denominators of fractions, and it takes 2 odd numbers at a time. So basically the first 2 lines here are calculating these odd numbers. It starts with a range, multiplies that range by 2, and then adds 1 to it to get the odd numbers. It then chunks these into 2 elements at a time, then takes the multiplication reduction, so basically the product of those 2 numbers. So for the first term, 1 over 3 times 5, you get 3 times 5 from the first chunk, and then you multiply those together. Then you take the inverse, you add all those up, and then that'll give you 1/8 of pi. So if you multiply it by 8, you'll end up with an approximation for pi, which is really neat. So after cleaning this up, I defined an explicit function called first n odds, so we can just make one call to this and it's a lot easier to read. Then we call chunks of, we replace the multiplication reduction, the fold multiplication 1x with product. So we're then mapping the product for each of the sublists in our list of lists. And then we've combined the inverse function with the multiplication by 8. So we don't need to have 2 separate lines for this. You can just divide 8 by x instead of 1 by x. And then last but not least, we redefine fold plus 0 to be sum. So you get something much nicer here. And I've increased it from 1,000 to 10,000 on this line, and you can see we got more accuracy. And as you saw, a short preview because I accidentally scrolled ahead a couple seconds ago. An alternative solution for this in Haskell is a little bit cleaner in my opinion. You have your approximation, you read from the bottom up, first n odds, chunks of 2. I think the syntax for their lambdas, or I guess this isn't even a lambda, this is just a composition of 2 different, a section and a function called product. You're combining product with 8 divided by the value that you're getting from chunks of 2. And then once we've done all this, we're just summing it up. And the last question from the first section of the third part of the first chapter is exercise 1.29, which we initially skipped and are now coming back to. And this problem states a lot. I'll just read the first bit. It says, Simpson's rule is a more accurate method of numerical integration than the method illustrated previously. Using Simpson's rule, the integral of a function f between a and b is approximated by h over 3, all multiplied by y0 plus 4 times y1 plus 2 times y2 plus 4 times y3, etc., all up until y of n, where h is equal to b minus a divided by n, and for some integer n, and yk is equal to the function past a plus k times h. And basically what it says is define a procedure function that can be used to use Simpson's rule in order to more accurately compute the integral of the cube function between 0 and 1, which we previously saw done in the book. So this is my solution for this problem. We're importing or requiring both threading and algorithms because that's my favorite way to solve these problems. And then we've got our function Simpson's integral that takes f, a, b, and n. So f is going to be the function that we're integrating, a and b are the bounds, and n is going to be the number of intervals in between those two bounds to determine our accuracy. And so I'm using something that's going to get introduced later in this chapter. Technically, they don't introduce let star, they just introduce let, but in the Berkeley corresponding lectures to this chapter part, the professor gets asked, how come we can't have dependencies within our let definition list? And he points out that you can, not with let, but with let star. So basically, let enables you to assign these temporary local variables. So we're assigning h to have the value of b plus a divided by n. So that's sort of like our discrete step between a and b. K is going to be the number of terms where the 4 and 2 alternate. So you can see in this formula, we basically have this 4, 2, 4, 2, etc., but it ends on a 4. So the coefficients on each of the values computed from our function are going to be 1, 4, 2, 4, 2, 4, 2. So the way I solve this is basically figuring out how many times 4 and 2 repeat, and that's to figure it out. You divide n by 2 and then subtract 1, and we'll call this k, and then we can basically just create a list of coefficients by appending 1 at the beginning, 4 and 1 at the end, and then a list of k for 2's. So you'll end up with 1, 4, 2, 4, 2, 4, 2, and then at the very end 4, 1. We can append these all together and then flatten them into a single list, and then we have our coefficients. So once we have h and coefficients, we have everything we need to figure out our solution using the threading macro and algorithm. So the first thing we do is we get all of the steps in between A and B, and note that you have to add a single value because we go from y0 to yn inclusive. So there's actually n plus 1 values here. So we are using range to get all those values, and range has an overload that takes the steps. So typically if you're just doing range of 1 to 10, it's going to step by 1. But if you give it a specific fractional value or a value larger than 1, it'll step by that value. So then we have all our basically x's that we're going to pass to our function f. So then we can map f over these values. And then what we need to do, so at this point, once we've done map f, we have all the values y0 to yn. Then we need to basically do a zip width. So multiply these y values with the coefficients 1, 4, 2, 4, 2, 4, 1, and we can do that with zip width. So zip width is basically a function that I've defined in the algorithms module that takes two lists and a binary operator and combines those two lists, two elements at a time, using the binary operator. So it's going to take our y values and our coefficients and multiply them together. Then we just need to add them all up and then divide and multiply it by h divided by 3, because that is what our formula says to do. And if you do this, you're going to be able to get the correct solution. So moving on to the second section of the last part of the first chapter, entitled Constructing Procedures Using Lambda. I believe this section is pretty short. It basically introduces the Lambda keyword, which we've been using up until this point, as typically you'll see it in my solutions as the actual Lambda Unicode character. But it's just saying that when we define a function, it's actually the same thing as defining the following. So you can explicitly put a lambda in here and an extra set of parentheses, and drop the parentheses around the function name and the parameter list, move the parameter list inside the lambda, and you'll have the same thing. And after it introduces the lambda keyword, it then introduces the let keyword. And I've sort of quasi-introduced this previously, but it just, once, as I said before, enables you to define local variables that'll exist during this scope. And note that there is a tiny tricky thing about this. If you're only defining one local variable, you still need the extra set of parentheses that would sort of define the list of locals that you are defining. So you can see here we're defining A and B, and we have a set of parentheses binding A to this expression and binding B to the value of this expression, and then we have parentheses outside of this as well. Even if you only have one, you still need this extra set of parentheses, which is something I ran into. And yeah, this is it for the let keyword. And I believe this is the only question or exercise from this second section. It says, suppose we define the procedure, define f with one parameter g, and then it applies g to 2. Then we have f square, which gives us 4, and f of lambda z times z plus 1 to z. So this would give us 6 because we're basically adding 1 to 2, which gives us 3, and then multiplying 2 to 3, which gives us 6. And then it says, what happens if we perversely ask the interpreter to evaluate the combination f of f? Explain. So using substitution, you can basically just walk through this. If we apply f to f, f here is going to get passed in, and so then we're going to apply f to 2. So then 2 is the proc in the next call to it. So then we're ending up with 2 applied to 2. However, 2 is a value. It's not a procedure or function that can be applied to something. So we're going to end up with a compiler error or interpreter error, basically saying that 2 is not a procedure, so you can't apply this to 2. Pretty straightforward. And that covers the second section. So that was pretty quick. So we're moving on to the third section, second last section of the last part of the first chapter. And that is procedures as general methods. So one of the first things that this section talks about is finding fixed points of functions. So it defines this as a number x is called a fixed point of a function f if x satisfies the equation f of x equals x. For some functions f, we can locate a fixed point by beginning with an initial guess and applying f repeatedly. So that's a neat trick. And it then goes on to give us the implementation or definition of this fixed point. So it defines a tolerance and then a fixed point f and then an initial guess or a first guess. And it's very similar to what we saw before with the square root. It's basically checking each time, is it close enough? Is it within the tolerance, less than the tolerance? If not, we're going to be trying over and over again. And this is a pretty neat way, and they use this to solve some problems upcoming. So exercise 1.35 states, show that the golden ratio is a fixed point of the transformation, the function x to 1 plus 1 over x, and use the fact to compute the golden ratio by means of the fixed point procedure. So this sounds more complicated than it is. We basically just have to take the fixed point procedure that we just saw and then apply 1 over 1x, or use the function 1 over 1x, 1 plus 1 over x as the f and give it an initial guess. So we use the function that was just defined, and then we pass using a lambda, lambda x, and then plus 1 with the sub-expression 1 divided by x, and then we give it an initial guess of 1.0, and then we get the following, 1.618, etc. And if you Google what the golden ratio is, this is very close to the actual value. And if we increase the tolerance or decrease the tolerance to a smaller value, it would get more and more accurate. The next exercise, 1.36, says modify the fixed point procedure so that it prints the sequence of approximations it generates using the new line and display primitives shown in exercise 1.22. Then find the solution to x to the power of x equals 1,000 by finding a fixed point of the function x equals f of x equals log of 1,000 over log of x. And it says you can use scheme's primitive log procedure. Compare the number of steps this takes with and without average damping. So I didn't use the average damping. I just compared the number of steps that it took in between finding the golden ratio and the log of 1,000 and the log over x. And if we take a look at the adjustments that we need to make, it's basically 2 lines just inside our try function right after our let definition of get next. We can just put in new line and display next, and then once we call this again to the golden ratio function and to the log 1000 over log x, you can see that the log 1000 over log x took a lot more steps than the golden ratio calculation did. And note that you can't use 1.0 with the log 1000 over log x. You need to use a different value. The next problem that we cover is exercise 1.37, and it defines an infinite continued fraction as an expression of the form f equals n over d plus n over d plus n3 over etc. And it basically asks us to implement this and then to calculate the value of 1 over the golden ratio by passing basically just constant ones as n's and d's. So if you want, you can read through the whole problem statement, but it says that if we replace the n's and d's with just ones, and you give it a number of steps k, you can approximate, using this infinite continued fraction, the value of the golden ratio. So let us go ahead and do that. It's actually pretty straightforward if you implement this recursively. Part B asks you to do it iteratively. But basically we have our continued fraction, we give it n and d, which are going to be higher order functions, and then k, which is a number of steps. Inside we check, is k equal to 1? If so, we just give it the last term, which is going to be n over d, and else we are going to do n over d plus a call to continued fraction with n and d, and then we're decrementing k. And then we can compute the value of this golden ratio by basically just passing it higher order functions that always return the constant 1. And note that because we're starting with k equal to whatever the value is, if it's 13 here, as I believe the number I passed it to get it accurate to 4 decimal points. But because we're starting at 13, technically, if n and d, the higher order functions, were actually to use k, this would break, which is why I have a little note. Note that this recursive solution only works when n and d ignore k. The part B is defining it iteratively, and this will work all the time. So somewhat similar to our recursive solution, except as always, we have our intermediate iterative function cf iter. Same if statement, if I is equal to k, then just return n over d. Otherwise, return n over d plus another call to the intermediate iterative function cf iter. And in this case, we're kicking off our iterative function with k equal to 1, so we're not decrementing, we're incrementing. And if we do the same thing here with 13, we get the same value. So that's good to see. The next problem we're looking at is exercise 1.38. And it states, in 1737, the Swiss mathematician Leonard Euler published a memoir, De Fractionibus Continuus, sounds like a Hogwarts enchantment, which included a continued fraction expansion for Euler's constant minus 2, where Euler's constant is the base of the natural logarithms. In this fraction, the n i's are all 1, and the di's are successively 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, and so on. And the question asks us to write a program that uses the continued fraction procedure from exercise 1.37 to approximate E based on Euler's expansion. So the key here, really, we've already defined continued fraction from exercise 1.37. The key is basically to just come up with a cute way of representing these values for D. And if you'll note, every third number starting from the second number is a multiple of 2. So if we can basically just, for all other numbers, just return the value 1, and for every third number starting at the second number, we can just basically divide the index accounting for the second offset by 3 and then multiply that by 2, and we'll have our sequence. So this is what our solution looks like. Note we have to add 2 to the value that this continued fraction is going to give us in order to get Euler's constant. But for the n's, we're just passing the hard-coded 1, And for the d's, we have this higher order function here in the form of a lambda, which checks if the remainder of I divided by 3 is equal to 2. So this 2 is because we're starting at the second position for the numbers that we want to apply a special 2 times sort of the index. We do the following. We add 1 to our index to basically get it to the number that will actually be divisible by 3. Then we divide by 3, and then we multiply by 2. Otherwise, we just return 1. And this will give us our sequence of 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, etc. And we use 13, similar to what we used for calculating the golden ratio, and then we get Euler's constant, which is fantastic. And this brings us to the end of the third section, which brings us to the last section of the last part of the first chapter, entitled Procedures as Returned Values. So we're not actually going to use this for any of the problems in this section, but I thought it's worth mentioning that it talks about Newton's method, and it alludes back to the earlier in the chapter when it was talking about square root and how square root procedure that they defined was actually a special case of Newton's method. And basically what this section introduces is that you can use the fixed point procedure to implement Newton's method. So as I said, we're not going to be using this for any of the exercises that we cover, but it's neat to know, and I believe some of the exercises that we don't cover do use this stuff. So if you want, go ahead and do those exercises and make use of these two functions. But with that being said, let's skip to the first exercise that we're doing, which is exercise 1.40, and it states, define a procedure cubic that can be expressed together with the Newton's method procedure in expressions of the form Newton's method cubic ABC1. So although it mentions Newton method, we don't actually need to do anything with it. We just need to define this cubic ABC in the form of a higher order function, or a function that can be passed as a higher order function to this Newton's method. And so the way that we're going to do this is just by taking this formula, x cubed plus ax squared plus bx plus c, and then defining cubic, which returns a function that takes a single parameter x and uses the formula that we just stated. So we've got the addition or the summation of x squared plus a, or x cubed plus a times x squared plus b times x plus c. And then when we pass this to Newton's method with an initial value, it will go ahead and solve this. So great. The next problem is exercise 1.41. Define a procedure double that takes a procedure of one argument as argument and returns a procedure that applies the original procedure twice. For example, if inc is a procedure that adds 1 to its argument, then double inc should be a procedure that adds 2. What value is returned by the following expression? Double double inside double inc 5. I had a problem with this question, and it's just that why are they calling this double? Like, they literally in the question say that for the original procedure that applies the original procedure twice. So really, this function should be called twice, not double. Double has the semantic meaning of like doubling a number, not doubling a procedure. Like when you are doing a procedure twice, it should be called twice. But anyway, c'est la vie. So if we walk through this, what is it doing? You have double double, which is going to end up as quadruple basically, and then double quadruple. So if you quadruple twice, you're going to end up doing something 16 times. And if you increment 16 times starting with 5, you end up with 21. The next problem, which is I believe the third last problem that we're going to cover, is exercise 1.42. Let f and g be two one-argument functions. The composition of f after g is defined to be the function x of f of g of x. Define a procedure compose that implements composition. For example, if inc is a procedure that adds 1 to its argument, composing or compose square inc of 6 is going to give us 49, because you're basically adding 1 and then squaring. So 6 plus 1 is 7, squared is 49. The solution to this is similar to the double function. We're just basically, instead of applying f twice, we're applying g first inside a set of parentheses, then applying f, and that is the composition of f and g. And sure enough, if we call compose with 2 lambdas, the first one that squares and the second one that adds 1, we end up with 49. Our second last exercise is exercise 1.43, which states if f is a numerical function and n is a positive integer, then we can form the nth repeated application of f, which is defined to be the function whose value at x is f of f of ... f of x. For example, if f is the function x plus 1, then the nth repeated application of f is the function x plus n. And then it goes on to give another example, but ultimately the question asks us to write a procedure that takes as inputs a procedure that computes f and a positive integer n and returns the procedure that computes the nth repeated application of f. Your procedure should be able to be used as follows: repeated square 2, in parentheses, applied to 5, which gives you 625. So this ultimately, when you square twice, you end up with something to the power of 4, and 5 to the power of 4 is going to be 5 times 5, which is 25, times 5 is 125, times 5 is 625. So it also gives you a hint at the bottom that says you may find it convenient to use compose from the previous exercise. And the solution for this is actually not that complicated given how long the question was. So here we have our function repeated, and it takes f, which is a function, and n, which is the number of times that it's going to be applied. And then we have an if expression in the predicate. We're checking if n is equal to 0. In the consequent, we're just returning a lambda that does nothing because in the base case, you want to do nothing. And then in the alternative, we are calling compose, passing it f for the first parameter or the argument, and then in the second argument, making a recursive call to repeated where we pass f once again and then n decremented by 1. And last but not least, exercise 1.44, which states the idea of smoothing a function is an important concept in signal processing. If f is a function and dx is some small number, then the smooth version of f is a function whose value at a point x is the average of f of x minus dx, f of x, and f of x plus dx. Write a procedure smooth that takes as input a procedure that computes f and returns a procedure that computes the smoothed f. So this is the solution for exercise 1.44. You can see we have a function that we were naming smoothed f that takes another function f and dx, which is the small number, and we're using a lambda and then the threading macro in order to define this function. So on the first line of our threading macro, we have created a list of x plus dx, and x minus dx. Then we are mapping f over those values. So effectively we have f of x plus dx, and f of x minus dx. And then once we have those three values, we're just averaging them. And we can see at the bottom here, we're testing this by mapping smoothed f over a lambda that is computing the square and then giving it a dx of a value of 1.0. And then we're mapping this smoothed f over the range of values from 0 to 9. And we can see that this is correct because for 0, we're going to end up with -1 squared, which is 1, 0 squared, which is 0, and 1 squared, which is 1, to average that over 3 elements is going to give you 2 over 3, which is 0.67. Same thing for the second value. We're going to end up with 0, 1, and 4, which is 5, divided by 3 is 1 2/3, which is the value that we have here as well. So that is the last exercise that we're covering in the last section of part 3 of chapter 1. The only other thing I want to cover is one thing that was highlighted in the MIT lecture 2 that corresponded to this section. And that is the following that was highlighted. So there was a slide that covered the 4 different criteria for being a first-class citizen in a programming language. And this is also highlighted in the book. So those 4 things are: they may be named by variables, they may be passed as arguments to procedures, and they may be returned as the results of procedures, and they may be included in data structures. So this, if you've ever heard of first-class citizens in programming languages, most or almost all functional programming languages, including Lisps and other languages like Haskell and Scala, they treat functions as first-class citizens, whereas many other sort of quote-unquote mainstream languages do not. And so if you've ever wondered what does it explicitly mean to be first-class, well, here is the list of criteria. And I went looking for a list of sort of first-class citizens cross programming languages, and I didn't find one, but I did find this list on Wikipedia, which is specifically talking about functions and the different types of functions that languages support. So we have higher order functions, those being functions that take functions as arguments, and those that return functions. Nested functions, which is, I believe, referring to sort of what they call lambdas, anonymous functions, function literals, blocks, etc. Different languages call them different things, and whether or not you can name those anonymous functions. So, for instance, in C++ 11, C++ got support for anonymous functions, which are called Lambda expressions, but you can also explicitly give those a name, thereby sort of naming your anonymous function. And then on the last column here, we've got non-local variables, which refers to, I guess, closures that can capture state, and then partial application. So this table is actually bigger on the Wikipedia page. There's a couple sections below this, but I could only fit sort of these three general categories on the screen: the ALGOL family, the C family, and the functional languages. Note that it's kind of funny that ALGOL and C are different, because ALGOL in many ways contributed to C++ and C, but it doesn't really matter. So you can see that functional languages, almost every single one except for Lisp, has support for every single one of these. And then if we look at the C family, almost all had support in one form or another for higher order functions. And then as the languages have evolved, they have started to adopt these features. So you can see Objective-C got blocks, I believe, in Objective-C 2.0. C++ got lambdas in C++ 11, and they got stood bind in C++ 11, which enables explicit partial application. So it's very ugly compared to what you can do in functional languages, but you can, if you have a function that adds two numbers together, you can create another function from that by binding explicitly a value to one of those parameters and then passing a placeholder for the other one to end up with a unary function that just adds a specified value to that number. And then Java, you can see they got support for lambdas in Java 8 as well. So this is a pretty widely known fact that functional languages have had this stuff from the get-go, but they've been inspiring the non-functional languages, and a lot of these languages are adopting them in later versions. And you can see newer languages like Rust and Go have this built in from the beginning. So Rust has lambdas, Go has what they call function literals, but it's the exact same thing as a lambda. So great to see that even in the non-functional languages, we're getting support for this stuff. And last but not least, in the footnote 64, it says the notion of first-class status of programming language elements is due to the British computer scientist Christopher Strikey. And this name did not ring a bell initially when I read the footnote, but then when I was watching the Berkeley corresponding lecture, the professor mentioned that Christopher Strikey was one of the co-founders of denotational semantics. And I had listened to one podcast on Haskellcast and two podcasts on Functional Geekery that had talked about denotational semantics. And I thought that I would do the same thing that I did in the first pre-recording where I gave a little bio on Alan J. Perlis. I would give a similar bio on Christopher Strikey. And potentially going forward, I'll either choose someone that's mentioned in the book or in one of the lectures, or just sort of randomly choose an adjacent person, like maybe one of the authors, and give a bio, because I think it's fascinating. So who is Christopher Strikey, the co-founder of denotational semantics, also known as Scott Strikey semantics? The Scott in the Scott Strikey is Dana Scott, who is a Turing Award winner. He also developed CPL, which I believe stands for the Combined Programming Language, which is a predecessor to BCPL, which is a predecessor to C. So CPL influenced BCPL, which ended up influencing C, which influenced many, many languages. Strikey went to King's College, which is the same school that Turing went to, Alan Turing. His influential set of lecture notes, The Fundamental Concepts in Programming Languages, formalized the distinction between L and R values and introduced the terminology ad hoc polymorphism, parametric polymorphism, and referential transparency. So ad hoc polymorphism is the technical term for function overloading. Parametric polymorphism, it's known as several different things across different languages, but it's basically a form of generic programming, the ability to have a generic or templated, depending on the language, type for your parameter of functions. So, for instance, Go is famously currently does not have support for parametric polymorphism. And an example of this is if you want, there's a maximum function to take a maximum of two numbers, but it only works for floats. So if you want to take the maximum of two integers, you first have to explicitly cast those integers to floats and then pass those values. Whereas in languages like Haskell, they have support for generic types and parametric polymorphism, and C++ has templates. So a lot of languages have facilities for basically specifying generic functions where you can have polymorphic types for your parameters. And referential transparency is just a very too fancy word term for basically pure functions. And last but not least, Strikey coined the term currying. He did not come up with the concept, but he is credited with coming up with the term currying. So neat to know. And as I was doing my research, I discovered that I'm not exactly sure what the relationship was, but Christopher Strikey apparently worked side by side with Alan Turing on a number of projects. Specifically, at one point, when I came across this book and the excerpts from it, it seems like they were working on a computer that was producing music, and it got like a lot of attention by the BBC. Anyways, I have purchased this book through my Audible subscription, and I will maybe add a review or something in one of the following pre-recordings in the upcoming weeks once I've finished it. That's it for today's pre-recording. As mentioned before, the links for the Programming Languages virtual meetup, the Twitter, the Discord, are all down in the description down below. If you have any questions, feel free to post them in the comment section, and I will do my best to answer all of them. Thanks for watching, and have a great day.